Today we are going to talk a little bit about polygons, which is going to use some of the things that we've been learning about earlier in this unit. It's part of the reason why we're talking about it. If we're going to talk about polygons, we need to talk a little bit about what a polygon is, and there's also some basic polygon vocabulary that you should know about. So that's the first part of your notes outline today. So we're going to zip through some quick polygon vocabulary, and then we're going to talk about some ways that you can use the things we've been learning about to do some calculating with polygons. So first things first, what is a polygon? So a polygon is a closed figure. So you've got kind of a yes and a no area down here. So something like that would not be a polygon because it's open. It needs to be a closed figure. So a closed figure, it also has to have straight sides. So that means something like this, a circle is not a polygon because it's not straight. And no intersecting lines. So intersecting lines are crossing lines. So that means something like that would also not be a polygon because the lines can't cross. So, something like a triangle, that's a polygon. You could have a really crazy looking polygon as long as it's all straight sides. So that's all straight sides, nothing intersects, and it's a closed shape. So it looks kind of crazy, but that's a polygon. So that's what a polygon is. Now, you can have a kind of crazy looking polygon like the one that I just drew, or you can have kind of a nice looking polygon like this triangle or maybe a square. So those are nice friendly looking polygons. So those are examples of a special type of polygon called a regular polygon. So the difference between a regular polygon and all the other polygons out there is a regular polygon has all of the sides the same length. And all the angles are the same measure. So to give you an example, a square, that's a regular polygon because all the angles are 90 degrees and all the sides are the same length. A rectangle, not a regular polygon because the sides are not all the same length. So that kind of gives you an example of one that is or isn't. So some polygons are also regular polygons. We could also name a polygon based off of how many sides it has. And some of these names are names that you probably already know because you've been using them, but we're going to review them. So if you have 3 sides, hopefully you already know, that is a triangle because tri means 3. And 4 sides, we did a lesson on that as well. A 4-sided shape is a quadrilateral. Quad means 4. A 5-sided shape is a pentagon. As penta means 5. 6-sided shape, hexagon. Hexa means 6. 7-sided shape. This one is one that not as many people know. So a lot of people know triangle, quadrilateral, pentagon, hexagon. So a 7-sided shape is called a heptagon. So hepta is the word that means 7. So heptagon. So that's one that maybe is less familiar because we don't see it as often. An 8-sided shape, you see those all the time. Stop signs are 8-sided shapes. Those are octagons. Octa means 8. And then 9-sided shape and 10-sided shape, those are also ones that are a little lesser known that not quite as many people can recall easily. So a 9-sided shape is a nonagon. So nona means 9. And a 10-sided shape, you might actually know the word for time without realizing it because we use it in other places in math. So the word decimal, because our number system's based off of 10. Deci means 10. So a 10-sided shape is we pronounce it a little bit differently, a decagon. But there's that same stem that you see in like the word decimal. It means 10. So a decagon is a 10-sided shape. So that is basic triangle vocabulary that you should know. So if you see a shape with any of those different numbers of sides, you should be able to name the shape, which is why we took a minute to run through it. So there is your quick polygon vocabulary review. So now that we're thinking about what a polygon is and the different names we can give to a polygon, we're going to look at some things that we can actually do to calculate with polygons. We learned that the angles in a triangle add to 180 degrees. We also learned that the angles in a quadrilateral add to 360 degrees. And we did some calculating with that. So we can extend that to other types of polygons. So the way we arrived at a quadrilateral being 360 degrees is because it has two 180 degree triangles in it. So this has two triangles. We can follow that same pattern. So the next shape over, this is a 5-sided shape. It's a pentagon. So this has 4 sides. This has 5 sides. So I can split this guy up into 3 different triangles. And all the angles of the triangle are part of the angles of the pentagon, because that's a pentagon. So that's important. So we want to use all the triangle angles. We don't want any dangling triangle angles that are not part of the pentagon's angles. So 6-sided shape, hexagon, I can keep extending that pattern. So I can divide a hexagon up into 4 different triangles. And this is a heptagon and then an octagon. So I can continue that same pattern. So if I split this guy up into a bunch of triangles, so that's going to split up into, if you count them, 5 different triangles. An octagon, if I divide it up, sorry, that was a little crooked, but you get the idea. We could split up into 1, 2, 3, 4, 5, 6 different triangles. And all of these, all of the angles of the triangle are also part of the angles of the polygon. So hopefully you're kind of seeing a pattern here. So however many sides the shape has, so a 4-sided shape has 2 triangles in it. A 5-sided shape has 3 triangles. A 6-sided shape has 4 triangles. So the number of triangles is always 2 less than the number of sides. And we know, so this is a 2 less than the number of sides. So we can use that to pull together a formula for what the angles in a polygon add up to, because we know that each of those triangles has 180 degrees in it. So if I take the number of sides and I take away 2, because there's always 2 less triangles than there are a number of sides, that gives me the number of triangles. And I know that each triangle has 180 degrees in it. So I can take the number of triangles and multiply by 180, because that's how many degrees are in each triangle. So that gives us a little formula that we can use to calculate the angles in any polygon. So we already knew a triangle is 180 and a quadrilateral is 360, but now we can do bigger shapes by extending that pattern. So just as an example, if we had a 15-sided shape, so following our pattern, a 15-sided shape, if you take away 2, you could make or divide that up into 13 triangles. And each of those 13 triangles is 180 degrees. So we can do 13 times 180 degrees. So that means if I had a 15-sided shape, the 15 angles in that shape would add up to 2,340 degrees. That's a lot of degrees, but it's also a very big shape. So that's how it works. So that's one thing you can do with the polygon, is figure out what's going on with the angles. So we know, or we could figure out what the angles in bigger shapes other than just triangles and quadrilaterals add up to. One last application that you are going to look at today, so we're zipping through a bunch of different things with polygons in this lesson today, is this thing called a tessellation. So a tessellation is made up of polygons, which is why we're talking about it while we're talking about polygons. So tessellation is a pattern where polygons fit together with no gaps or overlaps. So this kind of neat little pattern that you have a picture of in your notes, that's an example of a tessellation, because all of those pieces fit together perfectly. You know, so if I had something like this, maybe that's a piece and that's a piece and that's a piece. That would not be a tessellation because there's a gap right there. It doesn't go all the way around. So any point, so the vertex is basically any point where you got a bunch of shapes meeting. So that's a vertex. You also have like another vertex right here. There's a bunch of other ones. So the angles at each vertex of a tessellation shouldn't have any gaps, which means they should go all the way around and fill that whole space around the point without any gaps. So if I'm filling that whole space around the point, then that means all of those angles, those corners, angles of the shapes right there, should add up to 360 degrees. So if you look, this triangle corner and this guy and this guy and the two square corners, if I put them all together in that shape, they all add up to 360 degrees. They end up going all the way around that point perfectly. So we can use that to test whether or not we can make a tessellation with different types of polygons. So this is an example. So we want to know, can a tessellation be made using regular hexagons? So remember, a hexagon is a 6-sided shape. Now, we need to do a little bit of work. So we've got, so regular hexagon would look, this is a rough sketch, something like this. All 6 sides are the same. And we also know that regular means the angles are also the same. So if we can figure out what the angles in a hexagon add up to, then we can figure out how big each individual angle is by just dividing by 6. So if we do that, so using our rule, 6 minus 2 is 4 times 180. Gives us 720. So that's all 6 angles in this hexagon. So if I divide that by 6, then I get 120. So that means each of these hexagon angles is 120 degrees. So if I'm making a tessellation just using hexagons, what I need to figure out is if I make a vertex point, can I go all the way around that using just 120 degree angles? Because that's what I have to work with. So if we track that through, so 120, if I put another 120 degree angle next to it, that's going to be 240. If I put another 120 degree angle next to that, that's going to add up to 360. So that means, yes, these 120 degree hexagon angles I can use to go all the way around. So that means I can, so yes, I can make a tessellation using just regular hexagons. So if you wanted to actually draw it out, if you're curious what that would look like, so if you start with a hexagon, maybe here's my vertex point. So I'm going to put another hexagon up here. So there's one angle, there's the second angle. It's a very rough sketch. And now I'm going to get a third hexagon angle right there. So that means I'm going to need another hexagon kind of hanging out there. So it would look something like that. And we've got the math to back it up to show that all the angles right here add up exactly to 360 degrees. So I'm not going to have any gaps or overlaps. So tessellations, if you're wondering, well, great, why do I need to know about tessellation? If you look around your house, you probably have tessellations in your house. So if you have tile anywhere in your house, or hardwood flooring anywhere in your house, or like linoleum, vinyl flooring anywhere in your house, the siding on the outside of your house. So all of those different things are pieces that fit together perfectly. They're all tessellations. So tessellations are actually used a lot in everyday design to design the things in your house that you're sitting in right now. So that's a good practical application of a tessellation. So there you go. You got an introduction to what a polygon is, some basic polygon vocabulary, how to figure out what the angles in any size of polygon will add up to, and a little application of polygons, which is this idea of a tessellation. So you are going to have some practice problems today that are going to let you try using these things from your notes. So you need to double check and make sure that your notes are completely filled in for the day. And if they are, then you can go ahead and move on to today's